In this video, we are going to talk about linear approximation, also called linearization of functions. This is going to be a relatively brief video because we actually already know all the information we need to know. We just need to know that this is called linear approximation or linearization. So the basic idea is that we can use a tangent line to approximate any function that we want, as long as we're close enough to the point where the tangent line hits the curve. So, in other words, we can use the tangent line at the point A, f of A, as an approximation to the curve y equals f of x when x is near A. Now, this is only a good approximation for values that are really, really close to A. The further you get away from A, the worse the approximation is going to be. All that this is saying is if you take the graph of any function that you want and zoom in close enough to a particular point, the graph is going to start looking closer to a straight line, as long as you're zoomed in far enough. So remember, our tangent line when we wrote it in point slope form, looked like y minus y1 equals m times x minus x1. And then we can just add that y1 to the other side, and I'm going to rewrite it a little bit. So when I take that point slope form and rewrite it a little bit, we get y equals y1 plus m times x minus x1. Now, if we are talking about the point A and f of A, and we have our slope, which was given by the derivative of our function evaluated at A, this tangent line equation looks like y equals f of A plus f prime of A times x minus A. So all that this is our tangent line, just rewritten a little bit. Now, after we've looked at that, let me actually give you the definition of the linear approximation or the linearization of a function at A. The linear approximation or linearization of f of x near x equals A is f of x is approximately equal to f of A plus f prime of A times x minus A. And does that look familiar? Well, it should, because that's just the equation of our tangent line. We're just saying that our function f is approximately equal to our tangent line. So if you are asked to find a linear approximation for a function, or the linearization of a function, that's just another way of asking you to find the equation of the tangent line, which we've been doing for a long time now. So let's do an example. The important part about linearization is that you can use this approximation to estimate values rather than getting exact values. And we're going to do that in our first problem. So an example. Find the linearization of the function f of x equals the square root of x plus 3 at a a equals 1 and use this to approximate the square root of 3.98 and the square root of 4.05. So the first thing we should do is find the linearization. Then we can deal with figuring out how we're supposed to approximate these using our linearization. So let's start by finding the linearization. What we need in order to do the linearization is we need to know what f of a is, and we need to know what f prime of a is. And my a happens to be 1 for this problem. So let's start with f of 1. F of 1 is the square root of 1 plus 3, which we all know is square root of 4, which is 2. So I have f of 1 is 2. Now I need to find the derivative at 1 so that I have my slope. So remember, the function was the square root of x plus 3. I'm going to rewrite that as x plus 3 to the 1/2 power. Now when I find my derivative, I can use my chain rule. 1/2 comes down. My new power is 1 smaller, so it's negative 1/2. And then I multiply by the derivative of the inside. And the derivative of the inside just happens to be 1, so it doesn't really matter that much. And I'm going to rewrite this just to make it a little easier to look at. That negative 1/2 power is the same thing as a square root in the denominator. So there's my derivative. And what is my derivative at 1? Well, at 1, we have 1 over 2 times the square root of 1 plus 3, which that's going to be 1/4, because we have a square root of 4, which is 2, and so we have 2 times 2 in the denominator. So now I know everything I need to know to write the linearization of the function. My linearization is f of x is approximately equal to my f of a plus f prime of a times x minus a. Again, this is just your tangent line. So I get my f of x is approximately equal to my f of a, which was 2, plus my f prime of a, which was 1/4, times x minus a, which is 1. And I'm going to simplify this just because I can. This is 2 plus 1/4 x minus 1/4. Or I can use that my function is going to be approximately equal to 1/4 x plus 7/4. This is my linearization. So I'm approximating my function with 1/4 x plus 7/4. Now, remember what our function actually was. My function was the square root of x plus 3. So we have said that near 1, square root of x plus 3 is approximately equal to 1/4 x plus 7/4. Now is the rest of the problem. We need to approximate the square root of 3.98 and 4.05. Let's start with the square root of 3.98. Well, notice that the square root of 3.98 is the same thing as the square root of 0.98 plus 3, meaning that my x value is 0.98. So I can use my approximation to say that the square root of 3.98 is approximately equal to 1/4 times that x, 0.98, plus 7/4. This is equal to 7.98 over 4, which when you divide that out, you will get, where is it? There. 1.995 as your approximation. Now, some of you might be wondering, how good of an approximation is this? And if you actually type into your calculator, square root of 3.98, what you're going to get in the calculator is something like 1.9949937 something. So is this exactly equal to the square root of 3.98? No, it's not. But is it very, very close to what my calculator says it is? Yes. And it was something we were able to calculate. You can do this calculation by hand. You might not be able to do this one by hand. I know I can. So this is the answer for that first approximation. It's a pretty accurate approximation. Now we're going to do the same thing for the 4.05. So the square root of 4.05, that's equal to the square root of 1.05 plus 3. So that means my x value is 1.05. Notice in the previous approximation that we did, my x value was very close to 1. And this x value is also very close to 1. That's why we're getting good approximations. If I instead tried to use the square root of 100, well, that would be silly. We already know that one. Square root of like 111 using this approximation, it would not be a very good approximation because our x value would be very far away from 1. This works very nicely for numbers close to 1. So, using my approximation, I know the square root of 4.05 is approximately 1/4 times 1.05 plus 7/4. And that is equal to 8.05 over 4. And what is that? Well, this is 2.0125. That's my approximation. And again, if you want to know how accurate this is, go ahead and type square root of 4.05 in your calculator, and it will tell you 2.0124611.8-ish. And you can see that, again, we're super close. If I round this to 4 decimal places, it matches my approximation. So it is a very good estimate, as long as we're using values for x that are very close to 1. All right, so we've done an example finding a linearization and showed how using that linearization we can get values that are very close to the actual value of the function. Let's do one more example of a linear approximation. Let's find the linear approximation for f of x equals sine of x near x equals 0. Well, we have to remember, what are the things that we need in order to find our linear approximation? Well, your linear approximation is just your tangent line. So all we need is the value of the function at 0 and the value of the derivative at 0. So I need f of 0, which is sine of 0, and sine of 0 is 0. I'm also going to need my derivative. The derivative of sine of x is cosine of x. And so my derivative evaluated at 0 is cosine of 0, which is 1. So now I can write my linear approximation. remember that your f of x is going to be approximately equal to f of a plus f prime of a times x minus a. F of x was sine of x. F of a was 0. F prime of a is 1. And then I have x minus my a, and a was also 0. So what I get is sine of x is approximately equal to just x for values of x near 0. So this means that when you're very, very close to 0, sine of x and just x are very, very close to the same number. But we already knew that. This is the reason why we had already used the limit as x approaches 0 of sine of x over x equals 1. This was also saying as we get close to 0, sine of x and x are close to the same value. So we already actually knew this, but now we showed it using linear approximation. And that is all I have for you today. It's a really short video, but we already knew how to do linearization. We just didn't know it was called linearization. So if you have any questions, feel free to drop them below. Otherwise, you can also email me or come to office hours if you're a current student of mine. And I will see you in our next video.